Okay, let's dive right into this. Welcome to this explainer, where we're going to unravel the invisible, often totally misunderstood, but honestly magical technology that powers our modern workspaces. If you're the kind of person who loves figuring out how the digital world actually clicks together behind the scenes, well, you're in the exact right place. Today, we're demystifying enterprise Wi-Fi and looking at exactly how a massive wireless local area network, or WLAN, is actually built from the ground up.
So picture this for a second. You're on a super important Wi-Fi voice call on your phone. You walk from your desk on the third floor, hop into the elevator, stroll across the ground floor lobby, and finally grab a coffee in the cafeteria. And you didn't drop the call once? How is that even possible? I mean, think about it. If you walked that same distance down your street at home, your Wi-Fi would have disconnected, what, 3 houses ago? That right there brings us to our core problem. The seamless Wi-Fi mystery. Why traditional Wi-Fi just doesn't scale. You see, the way we set up Wi-Fi in our living rooms fundamentally doesn't work for a massive corporate campus. Standard Wi-Fi simply can't handle thousands of people constantly moving around. This comparison really nails why. On the left side, we have autonomous access points, basically your home router. It does everything all by itself. It's the router, the switch, the antenna, the whole shebang. Every access point is its own little island. Now imagine having to hand configure 500 of those across a building. It's an absolute scaling nightmare. Plus, users drop their connections when they roam between them, and the radio signals are constantly interfering with each other. But over on the right, we have the real enterprise solution: lightweight access points paired with a wireless LAN controller, or WLC. We're fundamentally dividing the labor here. We create one central brain to manage hundreds of drone antennas. That is the secret sauce that allows for seamless roaming, automatic power adjustments, and a network that can literally heal itself if an antenna randomly dies. Meet the wireless controller, the mastermind behind the curtain. So, how does this brain actually do its thing? The magic phrase you need to know is split MAC architecture. We are literally taking the traditional duties of an access point and slicing them right in half. The lightweight access points, those white boxes scattered across the office ceilings, they just handle the real-time radio frequency stuff, sending and receiving the actual invisible waves. Meanwhile, the wireless LAN controller handles all the heavy lifting, authentication, security, and deciding when your phone should roam from one antenna to the next. And they coordinate all of this continuously through secure, invisible digital tunnels called CAP-WAP tunnels. It's really just a beautifully orchestrated system. Which of course raises a pretty fascinating question. All this wireless data floating through the air is great, but eventually it has to hit a physical wire to reach the internet or your corporate servers. So, how does our mastermind controller actually plug into the physical network? Connecting the physical infrastructure, plugging the WLC into the matrix. Remember, this single box could be processing data for thousands of wireless users at the exact same time. A single standard cable just isn't going to cut it. So instead, we use something called a LAG, or a link aggregation group. We literally take all the physical ports on the back of the controller, let's say 4 individual high-speed ports, and we bundle them together in the software. To the network switch, it just looks like one massive, ultra-fast logical link. This gives us an enormous data highway, and absolutely crucially, redundancy. If one physical cable gets yanked out by accident, the highway just loses a lane, but the traffic keeps right on flowing. Seeing this setup in the real world is super cool. Take a look at this dashboard. This is the Cisco Wireless LAN Controller graphical user interface. If you look right in the middle of that green graphic, it gives us an instant visual confirmation of our physical ports. You can see ports 1 through 4 are grouped together and glowing green. They're active. It acts as a visual heartbeat for our physical connections to the wider network. But hold on, we've got another mini mystery to solve here. Okay, the physical cables are plugged in. But how does a specific wireless signal, say a user logging into the guest Wi-Fi, actually cross over and find its way to the correct segregated guest wired network? Translating wireless to wired, mapping the airwaves to the network. Answering that requires a very specific kind of translation. We have to map those invisible airwaves strictly to the physical network architecture. And to pull that off, we use a dynamic interface. Think of a dynamic interface as a logical translation bridge sitting right inside the controller. Its entire job is to say, hey, if a user connects to the engineering wireless network out there in the air, I need to seamlessly drop all their data into VLAN 100 on the wired network. It maps the wireless name, the SSID, directly to a secure, compartmentalized, wired VLAN. And here's exactly what building that bridge looks like. On this configuration screen, we are setting up the dynamic interface for our engineering team. You can see right there, we've assigned it to a VLAN identifier 100. We give the interface its own IP address so it actually exists on the network. And crucially, down near the bottom, we tell it where the DHCP server is. That way, the very second a user's phone connects to the Wi-Fi, this interface knows exactly who to ask to get that phone a valid IP address. Okay, our backend infrastructure is primed and ready. The brain is connected, the high-speed highways are built, and the translation bridges are in place. But if you pull out your phone right now, you won't see any Wi-Fi networks to join. So, how do we actually create the network the user taps on their screen? Configuring your new WLN, bringing the network to life. To launch an enterprise-grade wireless network, you really just follow 3 critical steps. Step 1, which you definitely do first for enterprise security, is telling the controller where your Radius authentication server is. Step 2 is what we literally just did, creating that dynamic interface translation bridge. And step 3 is the fun part, actually creating the new WLAN so we can start broadcasting it into the air. The process for this is incredibly straightforward. In the controller GUI, we simply tell it we want a new WLAN. We give it a profile name, which is really just for us IT folks to read in the back end, but then we enter the SSID. That text string right there, in this case engineering, that is the exact name that's going to pop up on laptops and smartphones across the entire campus. But wait, before you go crazy creating a unique Wi-Fi network for every single tiny department in your building, you need to hear this golden rule. You absolutely must limit the number of WLANs you broadcast. The hard maximum should be 5, but honestly, 3 or fewer is ideal. Why? Because every single wireless network you broadcast has to constantly shout its existence into the air using things called beacon frames. If you create 10 different Wi-Fi networks, your access points spend so much time just shouting out their names that they literally starve the channel. They eat up all the usable airtime, leaving 0 room for actual user data. So less is definitely more here. All right, assuming we're keeping our network count low and healthy, we go into the final edit screen for our new engineering WLAN. Notice that little checkbox right at the top, Status, Enabled. Checking that box is the moment of truth. Below that, we select the interface group. Basically, we choose the engineering translation bridge we built earlier. The second we check that Enable box and hit Apply, our master controller instantly reaches out to hundreds of access points and tells them all to start broadcasting the engineering network simultaneously. Boom. You suddenly have coverage across a massive building. But that introduces a pretty terrifying new problem. Unlike a copper cable that's hidden safely inside a locked office wall, your network data is now literally flying through the free space of the air. Anyone sitting out in their car in the parking lot can pick it up. So how do we keep unwanted guests out? Securing the airwaves, locking down the invisible data highway. We absolutely have to secure those airwaves, and enterprise security is no joke. First, we mandate WPA2 or WPA3 encryption. That ensures that even if someone intercepts the data out of thin air, it just looks like complete gibberish to them. Second, we don't use a single shared password like you do at home. We use 802.1x enterprise authentication tied to that Radius server. That means every single employee logs in with their own unique corporate credentials. And this next part, this is my absolute favorite fact in this entire explainer: client exclusion policies. Let's say a hacker tries to brute force your network by guessing thousands of passwords a second. The controller detects that unnatural behavior and simply locks their device out. Now, even if you set that lockout penalty to just 60 seconds, it completely breaks the attack. A brute force dictionary attack that would normally take 2 minutes to crack a password will suddenly take 15 years, just because of that tiny 60-second delay between attempts. I mean, that is breathtakingly effective. Which brings us to this final thought. The invisible complexity of the networks we walk through every day is staggering. What looks like a single connection is actually a beautifully orchestrated symphony of hardware and software. The next time you wander through a large building, streaming a video, or holding a voice call without dropping a single packet, I really hope you think about the master controller, the dynamic translation bridges, and the invisible CapWeb tunnels making it all happen behind the scenes. You're walking through a literal matrix of engineering perfection. But as these networks grow even larger, and as AI begins to automate these master controllers, we have to ask, what are the invisible highways of tomorrow going to look like? Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.